Okay, so here's where we left off last time. I just kind of barely scratched the surface. Just gave you a little bit of a teaser of something to think about concerning the polar coordinates function. So I made the suggestion, seemingly maybe a little weird, that we can take a completely different interpretation of these formulas that we use to convert from one coordinate system to another coordinate system. And the odd suggestion is to reinterpret them not as an algebraic tool for conversion between coordinates, but to think of them as being together a change of variables function. Right? So just to use just like in the change of variables method that we talked about last time. And I guess you could do this, right? I mean, there's two input variables, R and theta, and there's two output variables, X and Y. And so it fits the form, and you could do this. So if you do, note what's kind of convenient about this is there are some familiar but inconvenient domains, such as this one, which when you look at the corresponding domain over here in the R theta plane, you get a nice, convenient little rectangle. Right? And this is exactly the kind of pullback opportunity we're always going to look out for. A domain that we're likely to be interested in, which is undesirable in one way, and then pulling it back to a much more desirable domain. Rectangles, of course, being basically the most desirable domain you can think of. All right, now let me try to persuade you that this is what the pullback domain is. Let's think about these edges. What is that edge right there? Notice theta is equal to 0 everywhere on that edge. Theta is equal to 0 and R goes from 0 to 1. That is that edge. Okay, now let's think about this edge there. That edge has R equal to 1. Right? R is equal to 1 everywhere on that edge, and theta goes from 0 to pi over 2. That's that edge. Right? We can kind of keep going along. This edge, theta is equal to pi over 2. R goes from 0 to 1. That's that edge. And then what's this edge over here? Well, it's a little bit weird, but when you think about it, every point on this edge has R equal to 0. That means all the points on this edge go to where R is equal to 0. It's like, so in, what this function, this change of variables function does to this shape is it kind of takes the left edge here and it just pinches the whole left edge down to this single point and thus kind of fans out the rest of the rectangle to make that quartered disk. Okay. All right. So it's a great pullback opportunity. So the moral of the story here is a change of coordinates function can be a very good change of variables function. All right. Now, if you're going to use change of variables, you do have to know what the stretching factor is. Let's do that stretching factor calculation. Absolute value of the determinant of the Jacobian. That's how you compute the stretching factor. We talked about that last time. And here's the various partial derivatives. That's the Jacobian matrix. Right? And take the determinant, multiply it out, Pythagorean identity, and you get absolute value of R. And then you notice, you look up here to this picture, and you see that over the entire new domain that we're interested in, note that R is positive for all of them, or non-negative for all of them. So absolute value of R is equal to R in this case. Now, this is a very convenient little last second adjustment to be able to make. Very handy to be able to get rid of those absolute values. Of course, the catch, the thing that's, what do you have to be careful of in order to be able to do that? You just have to make sure that R is positive. So my advice is that even though you could get clever and think of a way to describe this region by using negative values of R and different values of theta, don't. Right? Always represent your region in the most convenient way possible, which is with positive R's and thetas, the natural sort of the thetas that you would like to describe the region by. Because that convenient choice will allow you an algebraic convenience as well. It's a win-win. It's just don't do anything weird with your polar coordinates. Okay, having done that, now here we go. Here's the pullback calculation. Our integral that we're interested in, for whatever reason. Now, why are we computing this double integral of some function f? I don't know, maybe we're computing the mass, maybe we're computing population, whatever. The integrand is appropriate to the application, whatever that might happen to be. But that integral, in doing the pullback, right, there's a stretching factor. The stretching factor we just got through computing is r. Right, and everything else is just plug in what you already know. X is r cosine theta. We already knew that. Y is r sine theta. We already knew that. Just plug those in. Here's your new integral. Real easy to compute with. Note the domain for this integral is our new rectangular pullback domain over here. So r goes from 0 to 1, theta goes from 0 to pi over 2. See how that works? It's a pretty big win. So sometimes change of coordinates formulas are great change of variables functions. Okay, all right. Now this calculation of the stretching factor, this always goes through the same way. It doesn't really matter what your domain is. Whatever domain you might have, if you're using the polar coordinates functions as your change of variables function, then it's always the same Jacobian. You're always going to get the same determinant. This calculation always works out exactly the same. So let's just remember that that's the stretching factor. And as such then, your dx dy will always be rewritten as r dr d theta. And I encourage you to just memorize this expression, r dr d theta. By the way, I also encourage, I think it's a really good idea, to think of this as a kind of a single thing. Right? You know, in the same way that we think of dx dy as being dA, I mean, okay, I suppose you could think of it as separate things, and if you're looking at it as a nested integral, then they're separate differentials. But we think of them as serving the role of creating the area. The double integral, they're dA. Well, r dr d theta is dA. I encourage thinking of it as just the polar version of this single thing, dA. Along those lines, I also encourage that when you're going to do this trick, when you're going to use the polar coordinates function as a change of variables function, write it down all together, all at the same time. Don't, please, I'm very, I think it's a great idea to avoid, don't just write dr d theta by itself as a kind of a way of, demarking, the end of the integral that you're writing down, and you'll get to what to put on the inside later. I think it's a bad idea. Don't hesitate to put the r in there. Write r dr d theta all at once. The reason for that is because when you get distracted with, oh, look, what's my bounds? What does my pullback domain look like? What's going on over there? You might forget. I've seen it happen a million times. And students have, everything works out great. They have their bounds. They plugged in correctly in the integrand, and they forgot to put the stretching factor of r in there. And it's tragic because it's a big deal, right? Putting this r in there is an important part of the calculation. All right. Okay, so single object, r dr d theta. Okay, so let's talk about how to do the same thing in cylindrical coordinates. Right? Cylindrical coordinates are a coordinate system. We have conversion formulas for cylindrical coordinates. Where did I write those down? Here we go. All right, there's our familiar formulas for x, y, and z in terms of cylindrical coordinates. Well, notice that again, I can do this as a three-dimensional change of variables function. I have x, y, and z as functions of r, theta, and z. View it as a change of variables function. By the way, stretching factor, easy to compute. The calculation's not the same, but it's really similar. It's what we did before. Of course, now we have a 3 by 3 Jacobian because it's three-dimensional change of variables. But unsurprisingly, the algebra works out very similarly. Absolute value of r. And again, As long as you just make the convenient choice of always choosing R to be positive, then you get the convenient simplification that you can lose the absolute values. So another win-win. Don't make any weird choices with your cylindrical coordinates either. And then you can go through the same kind of an argument. So here's a picture of a domain. Maybe I want to do an integral over this, whatever you'd call this thing, half solid cylinder, I guess. I don't know. Suppose that's a domain for an integral for whatever reason. Not a particularly unexpected or weird situation. That's our domain. I want to compute the mass of this, or whatever. Weird domain. You can kind of anticipate in the process of slicing it up. Somewhere I'm going to have to find like either y as a function of x and z, or x as a function of y and z. And there's going to be square roots in there because we have a kind of circular situation. So I anticipate square roots in the bounds. Square roots in the bounds means there will eventually be square roots in the integrand, which means we're going to have ugly integrals. Nobody wants that. Okay. So I claim that in the cylindrical coordinates change of variables function, this rectangle, this rectangular box is our pullback domain. And let's think about this one little piece at a time. Let's think first about this face. That face, you'll notice theta is equal to 0. R goes from 0 to 1. Z goes from 0 to 3. That's that. Now let's think about, let's move it over a little bit. That little slice, just, a little bit in the theta direction, but, still parallel to the focus slice. Well, theta's a little bit larger, but it's the same range of values of R, and it's the same range of values of Z. With theta a little bit larger, all that is that. It's like, so as you sort of slide over in R theta Z space, you're sort of rotating around a little bit in XYZ space. And this going around all the way over to theta equals pi has us end up there when theta is pi, like that. So this rectangular box kind of sweeps out this exact domain that we're interested in. Everybody see the process there? So this is another perfect situation for a pullback. If I'm interested in doing an integral on this domain, we will instead pull back, do an integral on this domain. Don't forget your stretching factor. And everything works out really nicely. Let's see, where do I have this? Yeah, here we go. So the stretching factor is right here, aka R. Everything else is just a matter of plugging in. X is our cosine theta, Y is our sine theta, Z is still Z. Nothing happens with Z's. And here's our very convenient bounds for our new box pullback domain. Right? And we have now got a relatively easy integral to work out. The bounds, at least, are no problem. Okay, you can do the same thing in spherical coordinates. Very often convenient. Again, don't forget we have these formulas for converting spherical to rectangular coordinates. Again, you can choose to view that as a function. You can view that as a change of variables function from rho phi theta space to xyz space. You can compute that Jacobian determinant. This is a little bit of an uglier calculation. Trig piles in. But this is a healthy exercise for everyone to do at least once in their lives. I encourage you to go through and compute this determinant. You notice I didn't do the algebra here. I left it for you all to work out on your own. Everybody does this once in their lives. This is y'all's turn. Right? And here's the good news. Pythagorean identities everywhere. There's just lots and lots of just massive simplifications that come about because you're going to notice as you group terms together and going through the algebra, group terms together, you're like, oh, look at this. Here's a sine squared plus a cosine squared. 1. Right? So that happens a lot. And notice how much this simplified. This simplified dramatically. Rho squared sine phi. There's a lot of simplifying. So there's your stretching factor. Now again, we have this issue of, don't forget the absolute values. How do we deal with those absolute values? Oh man, what are we going to... A lot of students make the mistake of thinking that the point is, well, okay, so in cylindrical coordinates and polar coordinates, I had to make a point of choosing R to be positive. And rho is kind of the spherical kind of equivalent of R. So the rule must be that I have to require rho to be positive. And of course, that's clearly irrelevant. Right, look at this expression. Who cares if rho is negative? Rho is negative? Fine. Still, rho squared is what I'm looking at. Then you do anything you want with rho. Right? What you have to be careful with is phi. You have to choose phi such that sine of phi is not negative. Now here's the good news. What you would like to do with phi, to avoid all of the geometric insanities that we saw back in chapter 1 of bending over backwards, turning around upside down, and all these weird things. You would like to choose phi to be between 0 and pi. Those are the intuitive, most satisfying values to choose for phi. And good news, when phi is between 0 and pi, sine phi is never negative. Right? So, yet again, good news. Just always make the most convenient choices possible about your spherical coordinates and your stretching factor. The object inside of the absolute values will never be negative, and you can lose the absolute values. Okay, so good news. Win-win. Let's consider a scenario like this one. And suppose our domain is a semi, let's see, what is that, a semi-ball, right? The upper half of a ball, solid ball. And you can imagine if you were to try to do an integral over this half ball, square roots are going to be all over the place. You might recall we did a whole ball, right? Back in the section on triple integrals, and there's square roots all over the place. And every time there's a square root in your bounds, that means that there's going to be square roots in the integrand of the next integral. Square roots in your integrand means nightmare of inconvenience of integration, right? Nobody wants this. Okay, so what we do, I observe that is the image of a much more desirable domain. Let me walk you through how you can see this. Let's think about that rectangle there. Theta is equal to 0 on that rectangle. Rho goes from 0 to 1. Phi goes from 0 to pi over 2. It's not too hard to persuade yourself that is that quarter disk right there. All right, and then keep moving over a little bit at a time. What happens when you move up a little bit? Well, now you have a slightly larger value of theta, but rho and phi doing the same things. And, well, that gives you, again, a kind of a rotated, that takes this quarter disk we were looking at and just kind of rotates it around the z-axis, however much this got lifted up. So, again, you can see as you slice higher and higher here, theta is just going to keep increasing and take you all the way around, thus sweeping out. Since we can make it all the way over, we're going to make it all the way over to 2 pi. Well, 2 pi lands right back on there where we had theta is equal to 0. Yeah? Everybody happy? Okay, so let's see here. Where did I do the calc? Here it is. So the stretching factor. Don't forget the stretching factor. Our new domain, that's the pullback domain that we just got through talking our way through. Rectangular domains of constant bounds. And don't forget x is rho sine phi cosine theta, y is rho sine phi sine theta, etc. And here's your new integral. just like with cylindrical coordinates and polar coordinates, I encourage you to think of this as a single thing. Write it down all at once. Don't spend a bunch of time, you write down d rho, d phi, d theta, and I'll come back to the stuff on the inside later and start thinking about your bounds and the geometry of it all and plugging in for the algebra of all of this. A bunch of other stuff to do, and then forget to write rho squared sine phi. So a great way to never forget it is to never write down the differentials without the stretching factor at the same time, right? So write this as a single thing. I encourage you, by the way, to memorize this as a single thing. Rho squared sine phi d rho d phi d theta. Rolls off the tongue actually pretty well, right? So memorize that as a single thing. Write it down as a single thing, and then you won't forget it. Okay, so this is, roughly speaking, this is how people do integrals in various coordinate systems. It's just that there's a geometric convenience that's very nice that I want to talk about. And so let me return us to first example we did, polar coordinates. We were interested in this domain here, this domain R, and we observed that we could pull it back to this domain, D, over here in the R theta plane. And then it's easy to write down the bounds. And so we did the bounds by, we're doing slicing, first theta slicing. All right. Theta goes from 0 to pi over 2. That gives us our theta bounds. Then we focus on a particular theta slice. And on a particular theta slice, R starts at 0. And R makes its way over to 1. And that gives you your R bounds. Okay. So the big observation I want to make here is just that this slicing process, all the steps in that slicing process, you can just, instead of drawing those slices over here, you can just draw the slices over here in XY world as a geometric alternative. And let's just see what those look like. Your first theta slice looks like that. As you continue your theta slicing, those slices just in XY world look like this, right? Constant values of theta, slightly larger. R still goes from 0 to 1. That's what those slices look like in XY world. Et cetera, et cetera. And the last slice is that. Right, so it's fine. If you really want it, it's unnecessarily awkward. We're about to conclude, but the slicing process of pulling back, looking at your new domain, and doing good old, plain old section 4.3 slicing up of your new domain is fine. But the conclusion we're seeing here is that you don't really need to draw this picture, because everything that you would do geometrically, the slicing process that you would put on this picture is a slicing process that you can already see on this picture. Right? So just do your slicing. This is what we call theta slices in the XY plane. Just do your theta slices as theta slices look in XY plane. And then, for a given theta slice, now, doing it in the sort of the traditional way, there's what a generic theta slice looks like. Here's what it looks like in the XY plane. The process of observing that R goes from 0 to 1, well, you can see those points also over here in the picture you already have. So what I encourage, roughly, is to realize that there is a pullback domain. Sure, there is a change of variables function happening. But just don't bother actually drawing. Because everything you need to see, you can see over here. Okay. Let's do another example. Let's see. Here we go. Suppose our domain is the top half of the unit disk. Okay, well, top half of the unit disk, here it is. Now, I don't want to actually draw the pullback domain. Notice I didn't even draw the change of variable function. I'm just drawing just the XY plane. I mean, yes, there is a r theta plane over here, and there's a change of variables function going to it. But we don't need to draw that one. We know it's there. We know everything we need to know about it. I can see here. So here's what I need to see about that change of variables function. There's my first theta slice, where theta is equal to 0. My continuing theta slices look like this, and they go, you know, on and on. And then my last theta slice looks like that. And it's just really easy to see that this means that theta goes from 0 to pi. I mean, if you want to draw the r theta picture, you can, but I mean, you're really doing a lot of make work there. The information we need is here. Okay. Whoops. So yeah, so theta, 0 to pi. Okay, now what about the r bounds? For a given value of theta, we know the range of values of theta now, so we're going to focus our attention on a single particular value of theta. On this particular value of theta, I want to know the range of values of r. Well, r starts there at the origin, which is where r is equal to 0. It ends at that point. That point's on this curve. That curve, well, this is the top half of the unit disk. The unit disk is where r is equal to 1. Right, so our r slicing of our theta slicing starts at 0, ends at 1. And that's what we have here then, our r bounds 0 to 1. Again, notice that I've written down my area form here. So the dA, I've written it down all at once. R d theta. Did not forget the r. Right. Be careful with that. By the way, here's another mistake that students make. Sometimes students take me a little bit too literally when I say, think of this as a single thing, and as such, students think of this as indivisibly a single thing. Like this r doesn't actually participate as part of the integrand. And I've had some students write down, I mean, you look at the algebra here, you can see we have r squared times r dr d theta. And some students will leave it as r squared. Well, no, I mean, look, the r, that's in the integrand. It's in there, right? It's the change of variable stretching factor. It's part of the integrand. We get r cubed here. And so don't make that mistake. I've seen that several times. Okay. By the way, here's a question you may be asking. You'll notice that I've put my differential, my dA, here as r dr d theta. Why did I do the differentials in that order? Why didn't I write r d theta dr? Just as well, you could do r d theta dr, right? I mean, shouldn't I be doing that instead? Here's the thing. It turns out that it's really rare for there to be a situation where that's actually a good choice. And really rare for it to be a better choice than this. So I came up with a couple of examples here where you might conceivably do it the other way. Yeah, here's one where I do the slicing d theta dr instead of dr d theta. It's a strange choice, though. It's a lot harder to draw the pictures. Let's see, where did the pictures go? Oh, I had a picture here somewhere. Yeah, you get some weird pictures. DR slices are semicircles like that. It's strange, and it's just so rare that it's useful that I'm just going to skip the whole thing. I would encourage you to say, just always, don't ever do this. Don't ever do r d theta dr. It's effectively never a good idea. Almost never. And so therefore, always do r dr d theta. Okay. Cylindrical coordinates, same deal. This is what slices look like in cylindrical coordinates. If you ask what is an r slice, if I fix a constant value of r, you get a cylinder. If I fix a constant value of theta, get a plane like that, a half plane hinged on the z-axis. All right, constant value of z, I get a horizontal plane like that. So this is what your slices look like, and again, you can make reasonable choices as to which way you want to go through your slicing process. There's really two most common reasonable choices for reasons not unlike those in polar coordinates. dr and d theta you usually want to have in this order and together. And so you can either do the dz on the outside, or you can do the dz on the inside. But basically these are your two choices. Take your pick. Depending on the situation, sometimes one's better than the other. But there's no reason to put the d theta before the dr, or to split up and put the dz in between. There's no reason to do any of that. Hardly ever. It's not worth talking about. Okay, so let's suppose that our domain is this. Right here we have an upside down cone. You might think of this as like a pile of sand, and someone's been pouring sand like from an hourglass. And it piles up like this. You know, it stacks up, and then it starts to fall around the sides, and it tends to get a roughly constant slope depending on what kind of sand you have. So I want this to be my domain for my integral. And it turns out cylindrical coordinates are great for this. You could do this in rectangular coordinates. It'd just be ugly. There's circles. That means there's be trig. Right? Square roots. That's going to be annoying. Right? Okay, so I'm going to do the dz slicing on the outside. So z slices first. In other words, like that. Range of values for z. Well, z starts at 0. Z ends up here at the top, wherever the top was. And let's see, in the statement of the question, the cone whose base is a unit disk in the xy plane and whose vertex is at 0, 0, 1. So yeah, z is equal to 1. Okay. So z goes from 0 to 1. Okay. And you can see that here, z, 0 to 1. Okay, now, for a given value of z, looking at a single z slice inside of there. Oh, by the way, what is my next variable? My next variable is, what am I doing there? Theta. I want to look at my range of values for theta. So I need to take theta slices. Keep in mind theta slices look like this. Whoa, hang on. Right, there's theta slices. Keep in mind though, I'm not interested in theta slices of the entire solid. I've already done my z slicing. I'm only interested in this z slice. So what I want are not theta slices of the solid. I want theta slices of the existing z slice. So I appeal to your geometric intuition. If you take a disk and if you slice it with a plane like that, the slice is going to be a little line segment. What values of theta are we interested in? In other words, what values of theta, which of these planes hinged on the z-axis, for what values of theta as you go around do you get cross sections? And well, it goes all the way around, so 0 to 2 pi. So theta goes from 0 to 2 pi. Everybody happy? All right, now we focus our attention not just on my z slice, not just on my theta slice of my z slice. Excuse me, just on my theta slice of my z slice. Sorry, I got ahead of So there's the z slice. Here's my theta slice of my z slice, and it's just on that green line segment now that I'm interested in the range of values of r. And r starts, what starts there on the axis, that's where r is equal to 0. It ends here on this surface. Whoops. What surface is that? Well, that surface, the point I'm interested in, is on this cone. And I'm going to leave it as an exercise for y'all to confirm that this cone has equation r plus z equals 1. Think that through. Notice that this has got a rotational symmetry around the z-axis. Right? So it ends up being r plus z equals 1. And let's see, what are we interested in about this point? I'm trying to find the r bounds. So I would like to know, whoops. For that point, I would like to know r, solve for r. My upper bound for r is 1 minus z. Everybody see what happened there? Okay. So, r goes from 0 to 1 minus z. All right. Spherical coordinates. This is the one that's geometrically probably the most challenging because these kinds of slices are a little bit weird, and well, spherical coordinates are just the weirdest ones, I think. The phi angle is a weird angle. Right? It's confusing. Okay, so constant value of rho looks like that. That's what a rho slice looks like. If you decide you want to start off doing slicing, your very first slice is on the outside. If you want to do rho as that outside variable, you're going to have to imagine the process of using a knife to cut in a spherical shape, a spherical slice. Not a lot of knives made like that, right? So this is a hard thing to visualize. You have to imagine having a curved knife and slicing like that. Right? It's very counterintuitive. A phi slice, a constant value of phi. Well, that's a cone, like that. And for different values of phi, right, you get either tall and skinny or short and wide cones. That's weird. Theta slices, of course. We already talked about those. Just like in cylindrical coordinates, they're just flat planes hinged on the z-axis. So because of the weirdness of these slices, it turns out that of your 6 different choices of different orders that you could slice, there's really only one of them that's ever reasonable. So always do it the same way. This is great news, right? So the bad news is 5 out of 6 are bad. The good news is you don't have to do them those bad 5 out of 6 ways. Just do it the easy way. The easy way is always the same, and that is we like that best. So we're going to do our d theta slicing on the outside. Having done that, let's see here. A rho slice would be curved even inside of that theta slice. But a phi slice is a straight line. So we do our phi slicing second. And that leaves, of course, only rho slicing. Rho slices they're still spheres, but how spheres intersect these things are just, well, we're just looking at the range of values of rho there. And so d rho, d phi, d theta. It's always this way. Correction. Always choose this. Okay. All right. And of course, don't forget your stretching factor. It's real easy to forget your stretching factor. So this is what you memorize as a single thing. Always write down all at once in one swoop. Rho squared sine theta, rho d theta, and then you can worry about what do the slices look like and what are the bounds and how do you convert the integrand and stuff like that after you've got that written down. Okay, so for example, And there's a bunch of examples on the exercise, obviously. You get a lot of practice with these, but we're interested in some triple integral. So again, maybe we're computing the mass of something. Maybe we're computing a population of whatever, or a concentration of some, gas, whatever it might be. And let's see, our domain is a ball of radius A, centered not at the origin, centered at 0, 0, A on the z-axis. Okay. So our domain is this. Again, you could do this in rectangular coordinates. There's going to be a massive pain doing this in rectangular coordinates. So let's not. Square roots everywhere. Nobody wants that. Okay, the very first thing we need to do is we need to write down the equation of that sphere. That's easy to do in rectangular coordinates. And, of course, y'all can refer back to Chapter 1 and note that if you have an equation of rectangular coordinates, you can just plug in and get the equation in spherical coordinates, which works out really nicely. Make sure you can do that, right? Again, we talked about that a long time ago, but it is a callback to long ago, namely about 3 weeks ago. Right? So anyway, in summer time, that's a long time ago. Okay, so right, so that's this. Keep in mind, note for a couple of minutes from now. That's the equation of our the bound on our domain. Okay, so let's go through and think about the slicing process. How would I slice this up? Remember, we have a choice. We always do rho squared sine phi d rho d phi d theta. We always do our theta slices first. Theta slices, let me do it like this. Theta slices are slices, half planes hinged on the z-axis. Now you just have to use your geometric intuition, but what happens when you take a ball and make a vertical slice through sort of the center axis, if you will. Just gotta, think it through. This is what that theta slice looks like, and our ball slice in question looks kind of like this. It's a half disc. By the way, you can actually do this. I think it's a great idea. Go to the grocery store, buy a stack of oranges and a knife. And while you're working on these kinds of questions, right? I mean, you can make yourself little three-dimensional models. Right? They're not that expensive. You get more fruit in your diet. It's a win-win. Right? Anyway, I think it's a good idea. So, but for the moment, since I don't have any oranges, I should have brought oranges. Okay, next year. I don't have to remember that. Yeah. Pass out oranges. That's right. But I can't pass out knives. Anyway, so I appeal to your geometric intuition. You get these half discs like that, right? Yeah, I can't do that either. Yeah. Oh my gosh, I should probably just withdraw the whole suggestion. Right? Yeah. I can see the headlines now. Okay, so that's what the slices look like, and you can think to yourself, okay, well, how far do these slices go? Well, you get your first slice over here where theta is equal to 0, and they kind of go all the way around to theta equals 2 pi. So grand total, theta goes from 0 to 2 pi. Right, and you just have to think about, what these things look like. So here we go. Theta, 0 to 2 pi. Okay, now, theta goes from 0 to 2 pi. Next question, what's the range of values of phi on a given theta slice? Now, you can do that on this picture. You can look at on this picture and start thinking about the ranges of values of phi. Thinking about phi cross-sections of this theta slice, as indicated on this picture. Let me confess, it's confusing, right? Because this slice, we're not looking straight at this slice. That slice is kind of curved. It's kind of turned we're looking at a side view in some sense of this slice. And it's it's easy to get confused with the geometry, even with a halfway decent drawing like I have here. Right? So I think it's a good idea, unless you're just really rock solid sure that you have a great picture in your mind of what you're looking at, redraw the theta slice. So this is that same theta slice. Here's what that cross section is. It's this, half disc. And it's just easier to see what's going on here. And you start drawing your, various different values of phi. There's phi equals 0. Here are increasing values of phi. Note phi slices are just lines, straight lines emanating out of the origin, right? And you keep getting cross sections until pi over 2. Your last sort of slice, after which you're just cutting air, right? Swing and miss, is at pi over 2. So phi goes from 0 to pi over 2. Now again, you can see that over here. It's just that what the picture looks like is harder to draw the picture. And it's just harder to see what's going on, at the origin, which is where all the phi slices are emanating from. Because the origin's kind of on the bottom. It's in fact kind of obscured by the front part of the sphere that we have drawn here. It's just harder to see it that way. And if you redraw the picture face on, I feel like it's easier to see. Okay, so I encourage students to do that. So 0 to pi over 2, and here we go. 0 to pi over 2. Yeah, everybody good? All right, so next we need to figure out what are the row bounds for a given theta slice. Here's our theta slice. Here's our phi slice of our theta slice. What's going on with rho? Excuse me. Well, we start at the origin where rho is 0. We go up until we exit the slice, because notice exiting that slice is where you exit the solid. Right? So what do I know about this point? That point's on what curve? Well, it's on this curve. That curve, though, don't forget, is really just part of that sphere. And that sphere, we've already gone to the trouble of finding the equation of. So this is the necessary algebra in which we need to solve for rho. Good news. It's already been solved for. That's nice. You won't always get that luck. In this case, fortunately, rho was already solved for. So that's our upper bound, 2a cosine phi. So rho goes from 0 to 2a cosine phi. Everybody see how that works? Questions? Yep.
If the sphere isn't centered at the origin, why are we still using z squared?
Why are we still using what?
Z squared.
Z squared.
And the integrand.
Oh, let's see. Let's look back at the original question. The question was that our integrand was given as x squared plus y squared plus z squared for no particular reason. I mean, why that's the integrand? Well, keep in mind, we never really addressed the question of why we're interested in this triple integral in the first place. But for whatever reason, we're interested in an integrand f, which is this. And maybe this represents density, or maybe it represents probability density function, or maybe it represents concentration or slide populations or whatever. Yeah. Yep, sure. Anybody else? Okay, so yeah, you're going to do a bunch of examples in the exercises. The processes are like this. There's a lot of artistic challenge in these, because there's no surprise when you're doing spherical coordinates. There's a lot of spheres, drawing spheres, and how spheres intersect things, and it is artistically non-trivial. Right? So it's unavoidably part of what the material is about. Right? So if you're not very good at drawing things, I encourage you to take that as a goal to figure out how can you get better at drawing things. Again, I'll repeat, I'm very happy to talk about that in office hours. I can't wave a magic wand and make you a great math figure drawer, but I can certainly point you in the right direction, give you some really good tips. Oh, hey, another thing I was going to mention. Those who have come and talked to me about this already, I've mentioned, but I wanted to make an announcement to everybody. On exams, you are welcome to bring in a straight edge. If you want to bring like a little ruler, right? The only catch is it can't have stuff written on it like equations. If it's got something trivial, elementary school level, if it's got the multiplication tables on it, fine, right? But if it's got trig equations on it, not okay, right? So anyway, but if you want to bring a little straight edge, it's great. I've even had a student bring in a compass for drawing circles. Fine, no problem. If you want to have the best figure on the test, I think that's just fine.
Would that be extra credit if we have the best figure?
That's an interesting idea. I never thought of that. I'll give it some thought. Yeah, probably not. But you certainly, I'll say this, is the better figures earn the appreciation of the grader because we can make more sense out of what you're doing. But of course, the big win is that you can see better what you're doing, and that's what's really helpful. Okay. Yeah. Okay, so moving along. Next section. We're going to talk about line integrals. So the problem that we want to address is something like this. Suppose we have a domain that is what I'm going to call dimensionally weird. And so this domain here is dimensionally weird. I have basically a curve. In space, though, is the thing. So it's kind of a one-dimensional domain in the sense that it's a curve and it has a length, right? If you wanted to, talk about the mass of something like this, you kind of ignore the little thickness. That's just part of what the rod is. But we talk about mass per unit length on something that's we're thinking of as being one-dimensional. You go to the hardware store and buy, chain or something. They talk about its, mass per unit length. They don't talk about the mass per unit volume and then make you figure out, look at the curves and how thick are these little pieces. And they just say, look, if you pull off 3 feet of this chain, here's how much it's going to weigh. So, natural way to think about things. So as a domain, having a one-dimensional curve in a 3-dimensional space is a weird domain. It's not a triple integral. Right? We're not talking about volumes here. We're not talking about, I'm going to take a volume and multiply by mass per unit volume. That's not what we're doing. So, it is in 3 space, and that makes you think triple integral, but it's a one-dimensional domain. That makes you think single variable integral. And it's neither exactly. This is weird. Okay, so how do we deal with this? We're going to define a new kind of an integral. This is what I'm going to call a line integral. I'm going to modify that in a moment. Line integral. And the idea is we're going to look at this scenario where we have this curve like that, and we're going to break it up into little pieces in the usual way. And now let's look at one of these little pieces, a specific piece, which I have magnified there for viewing convenience. On this little piece, I can talk about how big that piece is, talk about the size of the piece. This is a rip-off of what we've done earlier in Chapter 5, where we were talking about the length of a little piece of curve, or the area of a little piece of two-dimensional region, or volume of a tiny little sub-box, right? Size on a piece of curve is just length again. Right? So I can talk about what the size of it is. I'm going to call it delta S. Just have a name for it. And then I'm going to need to know where that piece is because, whatever I'm interested in doing an integral for, whatever reason I'm interested in doing an integral, there's going to be some associated integram. So maybe I need to know mass per unit length. Well, mass per unit length where? not just a mass per unit length might not be a constant. It might be different over here and different up there. So I need to know where this piece is. So I'm going to pick out some point, on this curve, some specific point that's the representative location for that piece. Okay, and having written that down, here's the idea. On each little piece, I'm going to multiply the size of the piece times the value of my integrand, appropriate to the application. Maybe I'm computing the mass. And I want to take length times mass per unit length at that location in that vicinity, right? So this would give me the mass of a little piece. Maybe I'm computing something else, so I have a different integrand, whatever. Whatever the answer to my question is on each little piece, I add up over all the pieces, take a limit as we slice more and more infinitely. Limit as n goes to infinity. Make round off errors go away, and we have a Riemann sum. Right? This is in this new weird situation that we're dealing with, this is the sort of the corresponding idea of the Riemann sum that we talked about back in section 1 of this chapter. Okay, so this is the notation we're going to use to represent it. It's pretty believable, I think, notation. This is just ds. It's just a shorthand to be suggestive of length, delta s, etc. Notice we're using as a subscript what the domain is, the curve, the path over which we're doing this integral. I can just make it a subscript. We've done that as a notation before. So really, this is extremely plausible notation. In fact, you might even say that you could have guessed this notation from this. Okay, so this is a line integral. Now, let me modify that term a little bit. I like to call this a scalar line integral. You can say line integral, and it's fine. And if you say a line integral, mass is computed as a line integral over the curve, everyone knows what you're talking about. There's no confusion. It's perfectly fine. Here's the issue. The issue is it turns out that there is a completely different concept that we're going to talk about next time. Let's see, either Monday or Tuesday. Completely different construction that computes completely different things, which, as it turns out, is also really naturally referred to as a line integral. So there's two different constructions that can and often are referred to by the same term. And I just think that's confusing. Right? So in order to distinguish these from each other, I like to put a little prefix modifier. This is the scalar line integral in the sense that this is a line integral where my integrand and my differential are both scalars. And it turns out, again, we'll see this later next week, turns out there is a completely different notion, we're not going to talk about it all today, where these are vectors. Very interesting conversation ensues, and there will be a related notion called a vector line integral. Yeah?
We're one to simply just say line integral.
Yeah.
More often than not, what we'll be referring to this scalar line integral, or is it just
it's both. Neither one is rare. They're both really important. And it is true that the context should always make it clear. If you ever say a line integral of a function, and if that function is a scalar valued function like this, then this is what they have to mean. So context will always make it clear. At the same time, it's just one of these things that kind of rubs the fur backwards on my head. I just feel better having distinct names for distinct concepts. But it's not really a problem. Yeah. Okay, how do we compute these things? Oh, I'm getting ahead of myself. Sorry. No, I'm getting ahead of myself. Let me do an example here. I'll come back to the other one. So the bent rod that we've been using as our metaphor to motivate what we've written down so far, how would I represent the mass of that rod given that I know density at a given position on the curve is given by some function. So mass per unit length is known. And the idea is you break up the path into little pieces. The total mass is the sum of the masses of little pieces. You add up over the entire curve. On each little piece, mass is mass per unit length times length. Okay, no surprise there. doesn't really matter if the little piece of length is level or angled or vertical. I mean, whatever, turned this way or at some weird angle. It doesn't matter. All that matters is how long is it and what's the mass per unit length. So line integral will answer that question for us for, what's the mass of the rod. Now, here's a little bit more hairy question. The idea here is we have a curve in R2, perhaps representing a driveway. By the way, when I wrote this question, I was living in a house that was well outside of the city limits, and it had a driveway that was long and curved, like in this exercise, and it snowed. So, this scenario actually came up for me. So, suppose you know what the depth of snow is as a function of location, and you want to know what's the total volume of snow that's on this driveway. Right? That was, again, what was going on in my mind. So here was the driveway. It was like 150 yards long. It was ridiculous. Yeah. And how much snow is there? So now keep in mind the scenario that we have here is that the snow is maybe deeper over there and maybe not as deep over here. Right? You can imagine snow might do this for whatever reason. And deeper snow, less deep snow, grand total, I don't care about snow that's not on the driveway, just the snow on the driveway, how much snow is there? And you can't just take the length of the curve and multiply by the depth of the snow, because the depth of snow is not constant. Okay. All right. So the idea is we're going to look at one little piece of the driveway at a time, a little piece of size ds. So given what ds is, by the way, the driveway is constant width for convenience. I know what the width is. That's like, 10 feet, whatever. And if I know how deep the snow is at that location, right? If I know the snow is that deep at that location, I can compute the total amount of snow sitting over this one little piece. Whatever that height is, depth, height, whatever you want to call it, multiplied by the width, multiplied by ds, that tells you how much snow, volume of snow there is sitting at that location. So, there you go. Total volume of snow over a piece of driveway of length ds is that. And, of course, the grand total amount of snow is just the sum of the little pieces of snow on all the little pieces of the driveway. And so you get another line integral, as it turns out. Okay. All right, so now, how do we compute these things? Right? So again, keep in mind we talked about this with double integrals and also with triple integrals. It's one thing to say, hey, I would like to look at a domain and chop it up into little pieces and therefore have a strategy for how to represent the answer to a hard problem with a Riemann sum. And that's great, right? But it's yet another thing entirely to be able to compute those things. And here, oh man, how are we going to, you look at a curved domain like this. What am I going to do? Take like vertical slices of it, or how am I going to? How am I going to get my hands on this? Right. So it turns out that we have a very broad stroke strategy already, and that is the change of variable strategy. If you have a domain that you don't like, view it as being the image of something, and then do a pullback. So here's our situation. Here's our domain that we don't like. I don't like this domain because it's dimensionally awkward. This is not a Calc 1 integral. Certainly not as it's written. It's not a triple integral. Certainly not a double integral. I don't know how to compute this Riemann sum. Right? So I don't like this domain. So our goal is going to be to try to figure out some way, kind of along the lines of change of variables, to view that as being the image of a different domain that I do like, and then talk about doing a pullback, just like in change of variables. Everybody see the kind of the strategy? This is a fingers crossed situation. I mean, I don't know if I can do this or what the details are going to be in this process of doing this, but this is our hopeful big picture strategy. All right, here's the good news. We already have this. If the picture looks familiar, good. All this picture is, viewing a curve as being the image of an interval on an axis. This is simply a parameterization. A parameterization is the kind of sort of change of variables function that we're looking for. So it's a pre-existing concept. We don't have to invent a whole new concept. We already have it. And of course, also, we all have a bunch of practice parameterizing things, right? So if you find yourself with a curve and you want to, compute the mass of the bent rod, or you want to compute the amount of snow you're going to have to shovel on the driveway, or whatever it ends up being, parameterize the curve. Okay. And then the idea will be that the integral that's defined, the integral that we have defined here, you do a pullback. You pull back through the parameterization and end up with an integral on the t-axis, good old Calc 1 integral that you can totally compute. All right. The missing ingredient here, of course, is the stretching factor. How do we compute the stretching factor? There we go. Got to figure out that stretching factor. Here, here we go. All right, so here's our curve that we have parameterized. I guess I'll just do this. That we have parameterized. Right. I want to consider a little piece of the t-axis. That's going to have as its image a little piece of the curve. They're not going to be the same size, probably. There's a width here of dt. But depending on the nature of the parameterization, maybe it's a parameterization that moves really fast, maybe it's a parameterization that moves really slow, whatever. Right? There's lots of different ways to parameterize a curve. Depending on the parameterization, it's not clear how long this corresponding piece of curve is going to be. What is this ds? That's what we want to know. More to the point, we want to know what's the factor that you multiply by dt to get this ds. But we're going to come at it by trying to compute ds. ds, you'll notice, now this is a geometric appeal, the length of that piece of curve I can approximate by my vector dx. dx is my linear approximation of position change, right? So it's a vector that's the linear approximation of how much is the output, for this parameterization. The actual output minus the input, something I try to approximate with a linear approximation. dx is my estimate of that increment. And so it's a differential approximating an increment. Okay, so I'd like to approximate dx. So I'd like to compute dx. Notice that this situation, this is a familiar situation. We have an input vector. My little input vector there is in the E1 direction. Well, of course it's in the E1 direction. We only have one direction on the t-axis, so I just put E1 just to make it a vector. And the length is dt. So E1 dt represents my input vector. I want to know what is the corresponding output vector. How do we relate input vectors and output vectors? Chapter 4, right? Lots of different ways to say the same thing, but generally speaking, broadly stroked, if you have an input vector, you want to know the corresponding output vector, derivative transformation. That's what the derivative transformation is. It relates input changes to output changes. Now, there's a simpler way to view this, and I'll come back to that in a moment, but I want to start us off with the more powerful general point of view here, which is that we are interested in an input change and the corresponding output change. There are going to be other situations coming up soon, probably not quite today, but where we're going to be interested in other. I have an input vector, I need an output vector. And I want to point out that they're all dealt with by the same object. The derivative transformation always allows us to relate these things. So I want to use the derivative transformation in this calculation here, trying to determine the stretching factor. There's my input vector E1 dt. Here's the dx, the output vector. The derivative transformation is what relates them. dt is a scalar, that factors out. We're left with we're just taking a derivative. That gives me velocity. So our nice punchline is that our differential, dx, or position differential, is just derivative times dt, which of course for a parametric curve means velocity times dt. And here's the simpler point of view. And for this single application only, the much easier way to argue this is, displacement is velocity times time. Well, of course it is. That's what velocity is. That's the purpose of velocity. So you can say displacement is velocity times time. Right? But I think it's valuable to see how this is an example of what you can compute with derivative transformations. And we'll see more of that next time. Okay, so our displacement is velocity times dt. We're interested in the magnitude. We want to know the magnitude of the displacement vector because we're looking for ds. ds is just the length of that little piece of curve. And so what I get is speed times dt. So distance equals speed times time. So again, it's really no surprise. It's kind of exactly what you would have expected. And that allows us to rewrite our line integral. Here's the line integral we're interested in computing. Integral of some function ds over a curve. Maybe this represents mass per unit length, whatever. Right. The pullback strategy, remember, is plug in your change of variables function. Here, position is a function of time. That's your parameter. You just literally plug in your parameterization. Don't forget that ds, distance, is speed times time. So your stretching factor, in other words, don't forget your stretching factor. Your stretching factor is speed, or namely the magnitude of the velocity vector, namely the magnitude of the derivative of the parameterization. There's your stretching factor. And that allows us to say that we've successfully pulled back on the domain. And so the original integral that was done over this undesirable curve now we've pulled back and we have an integral that's just from A to B, whatever those starting and ending values of t are on the t-axis. So we've successfully pulled back a line integral, brand new Riemann sum line integral, computing the answer to a question that we previously didn't have any means of dealing with, and we've rewritten it as a single variable. So these questions end up being kind of pluggy-chuggy. Pretty much the big trick is figure out your parameterization. Whatever your parameterization is, that tells you what to plug in there. That tells you what to take the derivative of to get your speed. That tells you what your starting and ending values of t are. Everything comes out of the parameterization. Right, yeah? Mm-hmm.
But in graph, probably we have to use the direction that is not x.
Say it one more time, I'm sorry.
If we take the function of x, we take like a piece that is not in the x direction, like for example in the y direction or in the z direction.
So yeah, what I'm using here is as my x. So I'm using x to represent position. Right, so that point there, x is x, y, z. So it's just x as a vector is representing all of the different coordinates. Yeah. Does that make sense?
Yeah.
Yeah.
Sorry.
Yeah. No worries. Yep. Easy to forget. Anybody else? So quick example, we have 45 seconds. We can do it. Well, you know what? If I try to make it, I won't finish, and then we'll go late, and I always go late, so let's quit early today. What do you say? This is a reasonable place to stop. So we'll do the example next time. I'm not assigning this section for today because I'd really like to do the example first, and I wouldn't be able to finish. Okay, I owe you all an email about the homework. We did finish coordinate systems today, integrals and coordinate systems, but we did not finish scalar line integrals. Okay, see y'all later.